Good morning, everyone. We'll continue this morning here in chapter 11. So let's start with this slide here that discusses the forces between ions and molecules, such as the forces between water and sodium and chloride ions, if we have sodium chloride dissolved in water. We've already talked about this a fair bit back in chapter 4 when we were talking about the process by which ionic compounds dissolve in water, is that the hydrogens, because they have this partial positive charge, that positive charge surrounds, the hydrogens surround the negative charge to take advantage of those positive-negative interactions. Now, you don't necessarily end up with a water sphere that's like stuck. You don't necessarily have waters that are permanently attached to the chloride. They'll still be moving around, bumping into each other, but every now and then a water will kind of stay relatively close to chloride for a few seconds, experience that electrostatic force of attraction between the partial positive and the hydrogens and the negative charge on chlorine, and then the waters flip. The negative charge on the oxygen surrounds the positive charge of sodium and something like sodium chloride when it dissolves in water. And so we end up with what we call these ion dipole forces of attraction. Now, these are generally very strong compared to the intermolecular forces. So if you're looking for comparably sized molecules, a dispersion force would be the weakest, and a dipole-dipole force would be stronger. If you have H bonding forces of a comparable size to those three, you would say the H bonding force would generally be stronger. But then the ion dipole force is even stronger because you now have full charges that are interacting with that dipole moment and the partial positive on water. And then you can also see that the ion dipole force would be proportional as you make a relationship to the size of the ions. It's going to be inversely proportional to the size of the ions. Make the ions smaller, you increase that force of attraction. So it's the same idea as lattice energies. Anything exchanging charge, we want to be smaller. So the smaller the ions, the greater the attractive force. And then if we have more highly charged ions, then that's even better. So a 2 plus 2 minus ion would experience a greater ion dipole force of attraction. So if we could increase the charges of the chloride and sodium, if we had calcium 2 plus, oxide 2 minus, we'd have a stronger ion dipole force between water and those more highly charged ions. I don't know where my writing went. Anyways, we'll move on to the next slide that then was comparing the relative magnitudes of these forces. That our dispersion forces are relatively smaller. So we have dispersion forces generally of these intermolecular forces are the weakest. Dipole-dipole forces a little bit stronger. Hydrogen bond forces a little bit larger as well. And then the dipole-dipole forces, the ion dipole forces of these four, the largest magnitude of them all. But these are still overall weaker than covalent bonds and still weaker than ionic bonds. So if you're ranking ionic bond strengths around 600 plus kJs per mole, we're only getting to about 50 or so kJs per mole for our ion dipole forces. And then if you're talking covalent bond strengths, those are in like the 200 to 400 kJ per mole range for single bonds. And so then atoms, molecules that are nonpolar only have dispersion forces. And again, you're going to be low in the dispersion force when the molecule is smaller. You'll be towards the higher side when the molecule is bigger. So dispersion forces can become quite large, but the molecule has to be big. And also has to have a lot of atoms. We'll see a comparison of molecule size in a couple slides. But then if we have polar molecules like HCl, CH3CN, those can't hydrogen bond those, so those are just polar molecules without hydrogen bonding capabilities. Then those are in between because they have the dipole-dipole force, but they still can have dispersion forces too. So we would still say like a liquid sample of HCl, the liquid molecules would be attracted by dispersion forces and the dipole-dipole force. If we had a sample of water or ammonia that was a liquid or solid, we would say the force of attraction that's holding the liquid or solid molecules together would be dispersion forces, dipole-dipole forces, and then also that H bonding force of attraction. And then something that I'm not quite sure why they don't include these on the slide for the ionic solids. I think ionic solids should still be thought of having the dipole-dipole force and the hydrogen bonding force of attraction between the water molecules within the sample. So if you have a sodium chloride compound dissolved in water, you're going to have the attractive force between the ion and the molecule of water. But then the water molecules still experience an attraction for themselves. So like your ion spheres are still waters that are linked together through their dipole-dipole force and hydrogen bonding forces of attraction. I think this slide was thinking the force of attraction between the ion and the molecule of water has still the dispersion force. Everything has dispersion forces, and then that ion dipole force. So I think they're just thinking between the ion and the molecule itself, those are the two forces of attraction, but the adjacent water molecules in the sample, of course, would still have their dipole-dipole and hydrogen bonding forces. Okay, so let's compare some different type of molecules. So if we're looking at propanol, propanol is the alcohol. If we just go back to nomenclature, propane is C3H8. So if you, just for a quick review, that's propane. So propanol would be C3H7 with the hydroxyl group. And so we didn't get into the nomenclature differences between 1 versus 2 propanol. We mentioned there's a slight difference of isomers if you have 1 propanol versus 2 propanol, but we didn't go through how to name those. So don't worry about having to name 1 versus 2 propanol for the final exam. But 1 propanol just puts that hydroxyl, that alcohol group on the first carbon. And so in this group here, we have that 1 hydrogen bond between the hydrogen and the oxygen. And we get the H bond because we have H directly attached to O. So all of our alcohols are like water. They have the hydrogen bonding force of attraction. They have dipole-dipole forces. And of course, they have dispersion forces. And so we have a relatively high boiling point as a result of having that H bonding force of attraction. And then something, not quite sure if we'll look at this. I think you'd see this more in Chem 1220. As you make the carbon chain longer, maybe we see it in this class too, but if you make the carbon chain longer and you go to butanol, you have more dispersion forces. So if you're comparing propanol to, say, butanol, where you have C4H10 is butane, so butanol would be C4H9, the hydroxyl group, that this boiling point would be greater. So if we're comparing the boiling points, the boiling point for butanol would be higher because we have a longer carbon chain, more dispersion forces. So the dispersion force increases. We have the same hydrogen bonding force of attraction, the same dipole-dipole force, or a similar dipole-dipole force to 1 propanol, but you put the hydroxyl group on C4H9, a longer carbon chain, we end up with a greater dispersion force, therefore a higher boiling point. So you can kind of see that as you start adding to the carbon chain, you're going to add to the boiling point of the alcohol just by virtue of having more dispersion forces. But now another way you can add to the boiling point would be to create a different molecule, but we want to compare molecules of similar size. So we want to keep the overall molar mass about the same. So we're at 60 AMU for 1 propanol, but then acetic acid turns out to have the same molar mass. So here we have the CH3 group, now a carbon double bond to oxygen, and then with the hydroxyl group here, this is that carboxylic acid group, if you remember from our nomenclature. So this is the acetic acid molecule with the COOH carboxylic acid group. Now, the thing that carboxylic acids have is the capabilities of forming 2 hydrogen bonds instead of just 1 in alcohols. So they pick up the capabilities of forming 2 intermolecular hydrogen bonds instead of just 1. And so then the impact that has in the boiling point is it increases the boiling point higher than just having 1 hydrogen bonding capability. So if you can have a molecule that can make 2 H bonds instead of 1, that's even better, even if you're at a comparable size. So the more H bonding capabilities, the better towards the boiling point. And that was also what made water have a higher boiling point than HF, if you recall, was water can form 2 H bonds. HF only had 1 hydrogen bond that it was forming. And then we also said, well, ammonia was interesting. It could form 3 because it has 3 hydrogens, but then the nitrogen just wasn't electronegative enough to make those bonds strong enough. So NH3 actually was the weakest of the 3 in terms of its boiling point, or the lowest of the 3. So let's compare all these molecules here and just get a sense of how their melting points and boiling points compare. As we're ranking boiling points, melting points generally are going to follow the same trend, because if we're going to have a substance go from a solid to a liquid, we have to break some of the intermolecular forces. When we go from liquid to gas, when we boil a substance, we're going to have to break a lot of the intermolecular forces. So we see probably a slightly bigger dependence of boiling point on intermolecular forces, but we still see a relationship between the melting point and the intermolecular forces. I bring this up because the first molecule I wanted to look at is glucose, where we have its listed melting point of 150 degrees C. Glucose is interesting. If you heat it up, it tends to caramelize. It tends to break its bonds and denature and turn into a different molecule. So it doesn't just go through a normal melting and boiling process like most liquids. Most liquids aren't going to break apart into some new molecule. So if you heat glucose or sugar up, it's going to turn into some other molecules once it browns in like your pan. If you're doing this in cooking, it's going to turn into some other compound that's not going to go back to glucose when you cool it back down. But it's going to melt at 150 degrees C, pretty high temperature. And then we have all of these hydroxyl groups within an alcohol. So we have the capabilities of 1, 2, 3, 4, 5 hydrogen bonding sites. We also have an oxygen here that has some polarity associated with it. So we have like a polar group. So we have a polar molecule, hydrogen bonding capabilities, a lot of hydrogen bonding capabilities. The molecular weight here is 180.2 grams per mole. So just to get a sense of how big the molecule is, let's compare that to a molecule that has roughly the same molar mass at 170 grams per mole and the compound of dodecane. So dodecane is the C11 hydrocarbon. I think that's what it is. C11H24. Does that make sense? Is that the right molar mass? I'm trying to. This is supposed to be the C12. Sorry, so this would be the C12H26 isomer. So C12H26, does that make sense? That's 12 times 12 plus 26. Yeah, that's 170. So this is the formula of dodecane here. And so dodecane with that molar mass, even though it only has dispersion forces because it's a nonpolar compound, it's nonpolar for kind of two key reasons. The CH bond's not very electronegative, and then also all the bonds are kind of opposite each other. It's one of those ways that the bonds are all kind of opposing each other. And the molecule ends up with is essentially a zero dipole moment, whereas look at the dipole moment. The polarity of glucose is really big. It's really high in terms of its dipole moment, so it's really polar, has hydrogen bonding capabilities, but take away the hydrogen bonding capabilities and the polarity, and you all of a sudden create a molecule that has a much lower, let's compare the melting point. The melting point is minus 10 degrees C compared to 150 degrees C. So that's the impact that hydrogen bonding has and polarity has on a molecule of increasing its melting point. If we could get a boiling point here for the compound, it would be very high. But like I said, it just turns into some other compound. But now notice, so dodecane actually has a pretty high boiling point. If you compare it to like water, which has hydrogen bonding capabilities, it's higher than water's boiling point. And that's because it has all the additive dispersion forces. If you took one of these molecules of dodecane and imagine another molecule on top of it, it has a lot of electrons. It has a relatively easier way to push those electrons around to induce dipole moments in itself due to having just that larger size. And it's also a long chain molecule. So having dodecane being one chain of carbon atoms is better than if we had it branch and have still a count of 12 carbons. But if we had a structure where we had the carbons that were, you'll see this in organic a little bit more, but if you had the carbons bridging off into like a more branch structure with the same kind of carbons, that weakens the bonding. That's going to weaken the intermolecular forces, and that would be worse for hydrogen bonding, or worse for dispersion forces, and it would lower the boiling point and the melting point. So we want longer chain molecules, more atoms. Now let's compare what happens when you look at bromine, Br2, where you take basically the mass of dodecane, but then you put it onto just 2 atoms instead of all 12 plus 26 atoms in dodecane. That has a big impact. We still have a zero dipole moment, so it's still perfectly a nonpolar molecule. And then the boiling point has a big change. So the boiling point lowers a lot. The melting point, interestingly, isn't so affected. That's why I kind of mentioned earlier that melting point is impacted a little bit by intermolecular forces, but the boiling point much more so by the intermolecular forces. So there's still a slight relationship between melting point and intermolecular forces, but a bigger relationship between the boiling points. And so we see the boiling point drop because the contact points are now lower. We have all, like the dodecane can almost like wrap itself around, so these structures can get closer because they can induce a dipole moment more easily than if we just had a smaller structure with 2 atoms, because we're going to have lower contact points. So imagine 2 bromines on top of each other, not as easy for them to exchange charge, so we end up with a lower boiling point. If you then reduce the mass down to just a single atom, we go to radon or xenon, the 2 noble gases, one slightly larger than bromine, one slightly smaller than bromine, but notice that the boiling point continues to drop. So we're dropping in boiling point, dropping a melting point as we go to smaller atoms, accumulating the mass onto a single point. This is kind of like branching the structure onto a single atom weakens the ability of those atoms to exchange charge. So having more atoms with the same mass is better than having fewer atoms with the same mass when we're comparing nonpolar molecules. So the dispersion force is larger for more atoms, more size, more molecular weight, longer chain, and more atoms. Okay, so let's take a look at the group of these molecules and try to see if we can pick out which one we think has the greatest boiling point. And so let's take a look at these examples. So I have CH3, CH2, 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 CH2OH. And so that's 1, 2, 3, 4, 5 carbons. First thing would be, can you name that compound? So do you guys remember what the name of that would be? So 5 carbons, penta, so that'd be pentane, would be the hydrocarbon. So if we had the CH3, CH2, 3 of these, CH3, that of course is pentane. So this would be pentanol. And if we're comparing that to the ammonia version, well, the ammonia version of that compound, that'd be an amine is what we call that. But the amine versus the alcohol, the NH2 version of the molecule has a weaker force of attraction because nitrogen is not as electronegative. So this is the same kind of issue that NH3 had a lower boiling point than water just because nitrogen wasn't as electronegative as oxygen. Now, again, this was tricky when we compared it to HF because you probably would have thought HF would continue, but water is still greater than HF because of the 2 hydrogen bonds. So oxygen is pretty special. It forms really strong hydrogen bonds. It can form more compounds than one. Remember, HF only forms that one key compound. Water can form a bunch of compounds that have hydroxyl groups on them that have that hydrogen bonding capability. But then the NH2 group just has a weaker H bond. And so we'd expect B to have a lower boiling point than A. If we're ranking these, A should probably be higher than B, just in terms of comparing the electronegativity difference of O versus N. If we're then looking at C and comparing that to version A and trying to think, okay, which one of those has the higher versus lower boiling point, this is what we call a branching point. So if we count the carbons 1, 2, 3, 4, 5, I still have 5 carbons. So I haven't changed the base formula. If I count up all the hydrogens, it should still be, so that's 6, 7, 8, 9, 10, 11. So it's still a C5H11 hydroxyl group. So it's the same formula. It's isomeric to compound A, but the issue is I've introduced a branching point. So when I have this structure, and if I'm thinking of the way this compound looks, I weaken the intermolecular forces because I have this branching point. And that's going to weaken, that's going to make 2 molecules. Imagine 2 of those molecules in C that are trying to get next to each other. They're going to have a weaker force of attraction due to that branching point. It's better to have a longer chain than a branched structure. And so that's going to make C have a lower boiling point than A. So A is winning out again compared to D. And then branching the amine is not going to help it. That's only going to hurt its boiling point for the same reason. So D should have a lower boiling point than B. Now we can't exactly rank order all 4 of these molecules, but we can certainly see that A here has the highest boiling point because it has the best, strongest hydrogen bonding capabilities due to having the more polar oxygen compared to nitrogen. In these examples, and we relate it maybe to water versus ammonia to come up with that explanation or that reasoning. And then it has the straighter chain hydrocarbon. So having a straight chain strengthens its intermolecular forces. So we would predict that pentanol, straight chain, would have a higher boiling point than compound C. All right, let's push forward. Which substance can only exhibit dispersion forces as its only intermolecular force of attraction? So this question is asking basically which of these molecules is nonpolar? Because nonpolar molecules only have the dispersion force of attraction. Polar molecules would have dispersion forces and dipole-dipole force. And then hydrogen bonding molecules would have all 3 of those key intermolecular forces. And so let's start with compound 2, because this one I think is pretty easy, that bromine is relatively electronegative. We get a dipole. Bromine's partial negative, hydrogen's partial positive. So this molecule here should have dipole-dipole forces on top of the dispersion force. So we can certainly roll out 2 because we know it's going to be a polar molecule. So 2 is polar, so it has that dipole-dipole force. So that's going to roll it out. 3 is a pretty obvious choice. Hydrocarbons aren't very electronegative because all their dipoles tend to either cancel, and the dipole moment's not very big to begin with. So our hydrocarbons are going to be nonpolar without having, hopefully, to think too hard. So we're only going to get the dispersion force because it's a nonpolar compound. So 3 is going to fit the bill. But then what about CH2Cl2? And one of the tricky parts here is sometimes, we're like, okay, let's start with the Lewis structure. So we write this Lewis structure. And then we do our lone pairs just to make sure we're doing our Lewis structure correctly. Maybe we count the electrons. So we have 4 plus 2 times 1, and then 2 times 7 for the chlorines. So that's a total of 20 valence electrons that should be in the Lewis structure. And then if I count up my electrons, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have the right number of electrons assigned. And then I could confuse myself here. If I'm looking at this structure, if I do this and think, oh, my 2 dipoles are opposing each other, this is nonpolar. Do you guys see how that's wrong? Why would that be wrong? Why is this compound not nonpolar? The real structure of the molecule isn't square planar. So these bonds really aren't 90 degrees. These bonds are really 109.5 because the molecule's tetrahedral. So the molecule really looks like a tetrahedron, and it doesn't really matter where I put the different bonds, but let's put the chlorines here, the hydrogens here. The hydrogens have a different dipole than the chlorines, so the chlorines have a charge that's not balanced by the 2 hydrogens. If I had CCl4, then that would be nonpolar. So the molecule like CCl4, if I replace those hydrogens with other chlorines, this would be nonpolar. But with the 2 hydrogens instead there, that makes CH2Cl2 polar. So dichloromethane is a polar molecule. We have to think about either its Lewis structure and its 3D shape. So when you're thinking of polarity, you always have to go to the actual true 3-dimensional shape. So if you have a flat Lewis structure, because that's how we like to write Lewis structures, just translate it into a 3D shape, either in your mind or on paper, and then think, oh, okay, I have this negative charge over here that's not balanced on the exact opposite end of the molecule. I want those 2 negative charges to be 180 degrees relative to each other, not 109.5 degrees. And so that means that we have a dipole-dipole force and dispersion force for 1, rolling it out. So only compound 3 here can have the dispersion force of attraction. Now, I mentioned earlier, you can't just rank random molecules. It would be hard to rank order these molecules on their boiling points because they have different molar masses, and so we have to have something in common. So whenever we're rank ordering boiling points, we have to really look more carefully at comparably sized molecules. Let's look at a couple properties that have a relationship to intermolecular forces. One of those is viscosity. Viscosity is the measure of the resistance to flow. So the higher the resistance to flow, the harder, the more resistant to flow the liquid is. So molasses has a high viscosity. So something like molasses, we can spell. Or motor oil, you can think of usual oils have a relatively high viscosity. Just think of something that has a resistance to flowing, like honey. And so something that has that nature is going to have a greater resistance to flow, and it's intermolecular forces that strengthen that resistance to flow. And so if you look at the comparison between hydrocarbons, you go heptane, octane, nonane, decane. As you just go to a longer chain hydrocarbon, as you go from the C7, or excuse me, the C6, so the carbon count here, 6 to 7, 8, 9 to 10 in our hydrocarbon, your viscosity is going up. So our viscosity is going from 3.26 times 10 to the minus 4 to 4.09 to 5.42, and then all the way up to 11.42 or 1.42 times 10 to the minus 3. So we're increasing our viscosity as we're increasing the intermolecular force. And we're increasing the intermolecular force by increasing the dispersion force by having a larger molecule. So we need molecules that have a strong attractive force to have a higher viscosity. Now, decane versus hexane, those viscosities are actually pretty low. Those just flow like ordinary liquids, and you wouldn't really notice too much of a difference between them. But you get into something that has a long chain of molecules that have like sugar groups hanging on them with those hydroxyl groups. That's what molasses is. So molasses is kind of like a molecule, like glucose has one like 6-membered carbon ring like we showed earlier with those 5 hydroxyl groups. Sucrose has 2 of them. Molasses has several chains of hydroxyl groups. And so you have a strong hydrogen bonding capability that then makes it harder for the liquid to flow because all those molecules are sticking to each other. But still not to the point, though, where the compound's a solid. So these would still be liquid in nature, where they haven't completely resisted flowing, and they still flow to some extent. Okay, so viscosity related to intermolecular forces. You increase intermolecular force, you increase that resistance to flow. Capillary action and surface tension have a relationship to intermolecular forces. And so let's take a look at what the two mean. So surface tension is the energy that it takes to break a surface. And so if we look at like a bug on water, it's able to kind of sit on water because it's able to not break the forces of attraction between water by having some sort of a mutual attractive force between whatever's on the legs of the insect and the water. And so there is a force that's attracting the water molecules, and you have to apply something that breaks that force in order to break the attractive force of the water molecules. And so the surface tension is the energy it takes to break that surface of water. And you can think surface tension will just increase and become stronger with intermolecular forces. So surface tension directly proportional also to intermolecular forces. Anything you do to strengthen the force of attraction of the liquid water molecules would increase the attractive force. Now, one thing that you get a relationship, though, is the temperature. If you start thinking of the temperature of the water, how does that impact the surface tension? If you have water that's colder, obviously if ice is frozen, you go to a really low temperature, you're not breaking the surface very easily of the water. So you can kind of get a sense, oh, the surface tension must be very high at low temperature, and then it must decrease as you go to higher temperatures. So it has an inverse relationship to temperature. Increase the temperature, you then weaken the surface tension. So it's going to be easier to break the surface of water if it's hotter than if it's colder, is the idea. Let's take a look at capillary action. So capillary action is, in one way, if you have like a capillary tube and you have a liquid in the tube, you get a meniscus. And if you get a meniscus like water, we know that we get this like upward meniscus. It's because the water has a mutual attractive force between what's in the glass. And so if water has an attraction to the capillary tube, it's going to have an upward meniscus because it's just saying, oh, I'm attracted to the walls of that capillary tube. And so the glass has SiO2 groups that look like this, and the SiO2 groups are polar, so they have that like polar attractive force. They have a lot of oxygens that then can, participate in that H bonding dipole-dipole force with water. So water has these attractive forces, so it forms that upward meniscus with a capillary tube. It does the same thing with like a plant stem. So a plant stem has molecules of like sugars in them, hydroxyl groups, mutual attractive force that's going to pull those water molecules upward. Obviously, that's really good for capillary action to draw water up a plant stem or up a tree or whatever. But then not every molecule in a capillary tube has a mutual attractive force with the capillary tube. One of those would be mercury. So mercury actually has a downward meniscus. So mercury would have a downward meniscus when the molecules actually have a repulsion with the molecules in the capillary tube. And so we get a downward meniscus if the molecule in the liquid has a repulsive force of attraction instead of a mutual attractive force. And so one of the words you see is adhesive force is just an attractive force. So water has an adhesive force. It adheres to the glass, so it has an upward meniscus. And then we get this repulsive force. We call that cohesion. The cohesion is the stickiness of the molecules together is stronger than the adhesion that they would have to the glass. So the question is the molecule or the atoms of the molecules in liquid, do they have a stronger attractive force together, or do they have a stronger attractive force to the glass? Which one's stronger? And here the mercury is happier staying with the mercury atoms, and it gets away, has that repulsive force with the SiO2, so we get the downward meniscus. And so Or capillary action is, of course, going to be directly proportional to mutually attractive intermolecular forces. So anything you can do to strengthen the intermolecular force of attraction between the liquid and the capillary tube would increase that capillary action, increase the meniscus, make it higher, and increase those attractive forces. Okay, so a quick summary so far is that for the most part, all these properties have a direct relationship on intermolecular forces. So if you look at melting point, generally you increase the intermolecular force of attraction. That means that there's going to be more forces that have to be broken to go from solid to liquid. So if we're going solid to liquid, we have to break intermolecular forces. So if you strengthen the intermolecular force, you increase the boiling point. So just try to think, is the relationship between intermolecular force and the property, is it directly related or inversely related? And we get a direct relationship, of course, between melting point and intermolecular forces. Obviously the same for boiling point. We have to break all the intermolecular forces for boiling point to increase. So if we strengthen intermolecular forces, we then therefore strengthen and increase the boiling point. We saw the same thing for these properties here, that if you increase intermolecular forces, you increase all of these properties as well. And then we have kind of a few more properties to go, and that is the enthalpies associated with phase changes. So we call those like the delta H of vaporization or the delta H of fusion, delta H of sublimation. We'll define those in a few moments. But these are the phase changes associated with the liquid to gas transition, the solid to liquid transition, and the direct solid to gas transition for sublimation. And so we'll see a relationship between those and intermolecular forces on the next couple slides. And then also we'll relate those to vapor pressure. Now vapor pressure, I'm just going to square this. This is going to be the one property that has an inverse relationship to intermolecular forces. And we'll see why in a couple slides. But that one there will go inverse, just to kind of call it out as the one property that's going inversely related to intermolecular forces. But these will also be directly related to intermolecular forces. So the enthalpy changes of vaporization, fusion, sublimation, those will all be directly related, we'll see in a slide or two here, to intermolecular forces. So let's look at our phase changes. And so I've been kind of mentioning this comparison here a few times, that if we go from solid to liquid and we're melting a substance, that we have to break some of the intermolecular forces. So usually our enthalpy change associated with solid to liquid is of smaller magnitude compared to the vaporization enthalpy. So usually this vaporization enthalpy, if we call this vaporization enthalpy X and call this one here Y, usually X is bigger than Y, because to go from liquid to gas, we have to break all the intermolecular forces, and here we only have to break some of the intermolecular forces. So melting involves breaking some intermolecular forces. Boiling, we have to then separate all the molecules from each other. So we have to break all the remaining intermolecular forces. So usually your delta H of fusion is relatively smaller. Enthalpy of vaporization, usually the magnitude is a fair bit bigger. And then we hopefully remember that the vaporization enthalpies, these should all have a delta H greater than 0. Same thing with the melting delta H. If we're going solid to liquid, liquid to gas, we have to have the substance absorb heat in the process. So those all require endothermic reactions. And so if we're going solid to liquid, liquid to gas, or direct solid to gas, that these all should have a delta H greater than 0. And if we recall, that's endothermic. So heat has to be absorbed to undergo those phase changes. And if you flip the reactions, if you go from gas to liquid, liquid to solid, or gas directly back to solid, then you just flip the sign. And those would all have delta H negative. So if we're going gas to liquid, liquid back to solid and freezing, or gas directly to solid, we call that deposition or depositing, that these all would then have a delta H less than 0, and that's exothermic. Let's compare some different molecules, enthalpies of fusion and vaporization and sublimation. So this slide here is comparing a few different molecules. Now, if you ask me, this slide's not great. This is from the book, so I'm just trying to go through a lot of like pictures from the textbook and with how the textbook presents this info. This slide would be a little bit better if they picked molecules that were more comparable in size to each other. But they pick kind of more randomly here. Maybe butane and diethyl ether compare a little bit closer than going back to water. But butane versus diethyl ether, relatively similar in size. And then you see that butane is only has the dispersion force of attraction. Diethyl ether has dispersion forces plus dipole-dipole force, but no H bonding forces. Water has the dispersion force, though a weaker dispersion force is because it's smaller, dipole-dipole force, and then H bonding forces. Let's worry about mercury in a minute. But for butane versus diethyl ether, you see that the enthalpy of fusion goes up a little bit. The enthalpy of vaporization goes up a little bit compared to butane because we have to overcome a stronger force of attraction. We have to overcome that now dipole-dipole force for this molecule. So slightly higher enthalpies of vaporization and fusion due to having now that dipole-dipole force of attraction. Now where water, like they probably could have been better to put like butanol or pentanol just to get a similar size molecule to those other ones here where we'd have a stronger dispersion force. But water has just a lower dispersion force because it's smaller. So if you notice its heat of fusion is kind of in the same ballpark, but that's just because it's a smaller molecule and it's not a good comparison. But its enthalpy of vaporization higher because it has that H bonding. And if we picked, again, a larger, like if we picked like C4H9OH, something that would be more comparable in size to those other molecules, then we would see that both those values would be a lot higher, that the enthalpy of fusion, enthalpy of vaporization would be a lot higher for those molecules. But now something interesting, because the fusion is solid to liquid, and then the liquid to gas is vaporization, if you go direct from solid to gas, and you follow Hess's law and you add these up, you should just be able to take the delta H of fusion and then add that to the delta H of vaporization to get your delta H of sublimation. So the delta H sublimation is just the summation of those other two individual enthalpies. So if you take 5 plus 24, that's our enthalpy of sublimation is 29. If you take 7 plus 29, that's where we're getting 36 for our enthalpy of sublimation of diethyl ether. 6 plus 41 is 47, so that's our enthalpy of sublimation. And this just follows from Hess's law. So if you take the summation of your fusion and vaporization reactions, you get the sublimation reaction. So you can just sum up the two enthalpies to get your enthalpy of sublimation. Now, mercury is pretty interesting because it has that strong metallic intermolecular force of attraction. Even though you look at mercury and say, okay, it's a liquid at room temperature compared to all of our other metals that are solid, it still has a strong metallic force of attraction. So therefore, it has a high enthalpy of fusion and a high enthalpy of vaporization. If you still add those together, you still get its enthalpy of sublimation. But mercury here has relatively high properties for these values here because it has metallic bonding. Okay, and like I said, it's kind of off the chart, so it's really hard to compare. It would have been really hard to for me to ask, can you rank order mercury compared to water? You'd probably say, I don't even know how to really make the comparison, but this slide here, I think it just meant to show mercury is pretty big, has still a relatively strong metallic bond. If mercury were smaller, it would have a stronger metallic bond, because we generally want to have smaller metals to have stronger metallic bonds. Yeah, Let's take a look at heating curves. So a heating curve kind of shows you if you're undergoing a series of temperature changes and phase changes, the heats that have to be absorbed to undergo those processes. So if you imagine ice, you take it out of the freezer. Most of our freezers at home are usually around 0 degrees C. And then obviously you're gonna melt at 32 degrees Fahrenheit. Our freezers are usually at 0 degrees Fahrenheit. And then it's going to melt at 32 degrees Fahrenheit, and 0 degrees Fahrenheit's about minus 10 to 15 degrees C. So your freezer, your ice, you'd pull it out of an ordinary freezer at home, it's a little bit below 0 degrees C, probably about 10 to 15 degrees below zero. And then the ice is going to have to warm up in order to reach its melting point. So there's a specific heat associated with ice. Different substances have different specific heat. So you might remember the specific heat of liquid water is 4.184 joules per gram Kelvin. that specific heat is going to be a little bit different for ice. So ice has its own specific heat. I'm not going to tell you, I don't even remember what it is, but it has a different specific heat than liquid water. So substances' specific heats are phase dependent, but water is going to have to absorb a little bit of heat to reach its melting point. This is why you put ice into a cup. It doesn't immediately melt because it's going to lose some of its heat, cool down the liquid that you put it into. It's going to stay ice. Some of it will melt, but not all of it usually, because you may only have to melt so much of it in order to undergo a phase change, or not a phase change, a temperature change of the liquid to reach the temperature of the ice. So some of the ice melts, some of it remains, and you can keep your drink cold for some period of time. But then if you have a sample and say, well, what if we want to totally melt the ice? Well, then you have to go through your phase change process. I know this value here, the delta H is on the previous slide. The delta H of fusion of water was, let me double check, I think it's 6 kJs per mole. It's like 6.01 if you're more precise. But that means that for every mole of water, it has to absorb 6 kilojoules in order to melt. And so you could quantify, if you have like a mole of water, how much heat does it take in order for it to melt? Well, it's going to have to absorb 6 kilojoules. And then if we're going to go from 0 to 100 degrees C, how much heat does it have to absorb? It has to absorb some heat in order to reach its boiling point. So if you put a pot of water on the stove, it's going to take it a while to go from room temperature to its boiling point, because it has to absorb the heat between whatever temperature you start and the temperature of the boiling point. And then if you think, well, how long is it going to take for that pot of water to sit on the stove and turn into steam and evaporate all the water? Well, you're probably going to have to sit there for a while. So you're going to have to, if it took you, if you're imagining, heating 25-degree water to its boiling point takes 10 minutes on an ordinary stove, it's probably going to take 10 to 20 times that amount of time to totally boil your pot of water and completely vaporize, because the water has to undergo this phase change process, which is 44 kJs per mole. 41 kJs per mole. And so water has to absorb more heat in order to break all of its remaining intermolecular forces and to turn into water vapor. And then you could continue, if you had a closed system, you could keep heating the water vapor and turn it into steam. You could have like a Instant Pot or like a pressure cooker where you have an enclosed system, and then you're just pressurizing the water, having steam present at a higher temperature than the boiling point of water. And so then you can continue heating, and then this would just be the specific heat of gaseous water. So in other words, you can imagine that in order to change water from one temperature to another requires us to know like our different specific heats, or just to imagine there's different specific heats for different phases, there's phase change enthalpies, but the biggest magnitude of all is that enthalpy of vaporization. So it takes a lot of energy to go through the gas to liquid transition, or the liquid to gas transition, because we're breaking a lot of intermolecular forces. We're only breaking some of the intermolecular forces in this process. We're breaking some of them here, so those are relatively smaller magnitudes compared to the vaporization change. There are problems that are math here. We're not going to get into the math problems. So don't worry about me saying, okay, you have 25 grams of ice. How much heat does it take to vaporize into steam at whatever temperature? Those problems are pretty boring. They're just math heavy. You might see some of those in the textbook, but don't worry about the math problem associated with heating curves. I just wanted you to see kind of the idea that in order to undergo a change in temperature, there's sort of like 5 key points. There's the temperature changes of the different phases, and then there's also just the phase change enthalpies as well. Let's talk about vapor pressure. So vapor pressure is that one property I mentioned earlier that goes inversely proportional to intermolecular forces, and you may wonder at first, well, why would that be? Well, let's think a little bit about what vapor pressure is. Vapor pressure can be thought of in a few ways. One way could be if you you have an empty container that's evacuated in terms of its pressure. So let's say we have like an empty flask. Let's even say we had a vacuum pump evacuate pressure from the flask, and then we add ethanol into the flask, and we're going to add some liquid ethanol into the flask. And the moment that ethanol hits the flask, there's like nothing else in the gas phase, in the air, or not in the air, in the volume above the liquid, there's nothing there. So the ethanol can escape, it can vaporize. I think we know ethanol has a vapor pressure. If you imagine the smell of ethanol, if you've ever smelled a bottle of alcohol, you can pick up the odor. You're smelling the vapors coming off because the substance has some natural ability to lose molecules into the gas phase that you're smelling. And then those molecules are going to occupy the container, and eventually they're going to reach an equilibrium whenever there's as many molecules that can escape from the surface and then hit the gas phase. And then that pressure that you have then exerting on the walls of the container is what we call the vapor pressure. So if you can measure that pressure of the sample, if you had a pressure gauge on here, you can then determine, oh, okay, at some temperature, that would be the vapor pressure of ethanol. And if you then thought, if I changed ethanol to a liquid that had a stronger intermolecular force, if you had a liquid that could really have a stronger force of attraction, do you think the vapor pressure would go up or down? It'd probably go down because the vapors, like the molecules wouldn't like release into the gas phase as readily. The stronger the intermolecular force, the fewer the molecules that are going to be able to escape. So the stronger the force, the fewer the molecules that hit the gas phase, the lower the vapor pressure. And then the same thing would happen if we add a liquid that had a lower intermolecular force, weaker attractive force. If we added something like that just didn't have the hydrogen bonding force of attraction, that was still a liquid at room temperature, like diethyl ether, the diethyl ether is going to readily vaporize because there's really not a strong force holding those molecules together. So if we then think about weakening the intermolecular force, we're going to increase the vapor pressure as a result because more molecules can then escape into the gas phase more readily. So vapor pressure can also, I like this example sometimes. It may not work so well because this is probably not super hot coffee anymore. But when you fill your mug with coffee and then you enclose it and then maybe like shake it up and you hear that hissing sound. The hiss is like, we started with a container that was at atmospheric pressure. We have a hot liquid in it. Water has a vapor pressure. Hot water has an even higher vapor pressure. And then whether or not we shake, like by shaking it is just allowing the sample to vaporize more readily. We then increase the temperature of whatever air was in here too. So we were taking air that was at room temperature, or at least when we first pour coffee into a room temperature cup, the air above it's at room temperature. Then you mix it up real quick, that air increases in temperature, the pressure goes up, right, from the ideal gas law. And then we're also vaporizing some of the water molecules because they're hot, so we're having then the increase in pressure. So we're just pressurizing, do the ideal gas law and the vapor pressure of water. And that's the sound you hear when you first mix a cup. And then it goes, like if you keep doing it, you don't hear the hiss anymore because it's already hot, the sample's already vaporized, it's already at its natural vapor pressure, so you're not seeing an increase in pressure. So you can see it with an ordinary coffee cup too. So let's think of the relationship to temperature. So how does temperature impact vapor pressure? Well, we're just kind of like mentioning that at a warmer temperature, we're going to expect there to be more vaporous molecules because they have more energy to escape the liquid. So if we increase the temperature of a liquid sample, the molecules have a higher kinetic energy. That's just like at any sample. Higher temperature, higher kinetic energy. Kinetic energy is a measure of temperature. So if the molecules have a higher kinetic energy, then they have a higher velocity. So this molecule's moving around faster. They then can escape the liquid more readily. So they have more energy to be able to overcome that surface tension, to overcome the forces of attraction holding the liquid together. And so then another thought is once they have enough energy, like if you imagine the average kinetic energy now is a greater energy than what the surface tension is, the surface starts to break. That's boiling. That's this sample bumping and the molecules leaving readily the surface. So whenever the molecules have enough energy, we then see this as a boiling event and the sample's then hitting the gas phase and we see the boiling event take place. So as temperature goes up, our vapor pressure goes up. So we're then approaching the boiling point of a liquid. And then an interesting thing happened, this might be defined on another slide, but boiling point is defined as the point at which the vapor pressure is atmospheric pressure. So when your liquid finally reaches, like if you start with like liquid water, relatively low vapor pressure, like well below atmospheric pressure. So if you have like room temperature water, it's around like on the millimeter of mercury scale, it's like 24, I think, millimeters of mercury at 25 degrees C, somewhere in that ballpark. And so that's lower than 760. As we approach the boiling point of water, the vapor pressure is going up. As soon as we hit 100 degrees C, guess what the vapor pressure of water is? Does anybody want to guess? 100 degrees C, what's the vapor pressure of water at 100 degrees C? Any guesses? 760 millimeters of mercury? The standard atmospheric pressure is 760, so water at 100 degrees C has a vapor pressure of 760 millimeters of mercury. And so think of it like this. Think of vapor pressure is the pressure that the liquid's going to release into the atmosphere, and then the atmosphere is pressing back down on the liquid. And so if we have a vapor pressure below atmospheric pressure, we have a liquid. And as soon as that vapor pressure goes beyond atmospheric pressure, then the liquid goes into the gas phase and it becomes a gas. So as soon as we go to a vapor pressure greater than the pressure holding the liquid together, it boils. So we can think of vapor pressure, temperature comparison. So lower temperature versus higher temperature, we can kind of think just from our Boltzmann distribution, just from our velocity distribution from chapter 10, we know at a higher temperature, on average, molecules have a higher velocity. Now I know this graph is actually taken from a gas chapter, and we're thinking of liquid molecules' average kinetic energy, but as a liquid, as the molecules in a liquid have a high enough kinetic energy, then they can escape the surface, and so the molecules that have a high enough kinetic energy go into the gas phase and can escape into vapors, and then the molecules that have a lower velocity stay as a liquid, and as soon as the molecules have enough kinetic energy where they all release into the gas phase, we then have boiling. So as we increase temperature, we have more molecules that have enough energy to escape into the gas phase. This slide here is now comparing vapor pressure curves for different types of liquids. So let's start with water, because that's one we were talking about earlier. So 100 degrees C, notice 760 millimeters of mercury. So that's our standard atmospheric pressure. So we call that the normal boiling point. So the normal boiling point of water, 100 degrees C. Vapor pressure is related to intermolecular forces and temperature. If we increase intermolecular forces, we lower the, if we increase intermolecular forces, we're going to lower the vapor pressure as a result. So we remember that relationship. And then our standard boiling point, this is what we were defining earlier. Our standard boiling point is the point at which our vapor pressure equals atmospheric pressure. So for our standard atmospheric pressure, 760, that's where we get our normal 100 degrees C boiling point for water. Now we lower the temperature, so we're looking at vapor pressure versus temperature. So if we lower the temperature, we're lowering the vapor pressure. And so at room temperature, we're somewhere around 25-ish millimeters of mercury. So really low vapor pressure for water. Now, if we go to ethanol is hard to compare to water, but ethanol has just one hydrogen bond. So it has a lower boiling point. If you keep increasing the carbon chain, you're gonna end up increasing so you can go beyond the boiling point of water, you're just gonna need a longer and longer carbon chain. So you get the like propanol or butanol, you'll go above the boiling point of water. So I don't know if I just asked you to predict ethanol versus water, which one has the lower boiling point? I honestly don't think you can make that comparison because they have different sizes. You'd be thinking, well, one has a weaker hydrogen bonding force, but has a greater dispersion force. But it turns out that ethanol has the lower boiling point and it has a lower set of a higher vapor pressure at all temperatures compared to water because it has a weaker intermolecular force. Since it has a lower boiling point, weaker intermolecular forces, and so then that's going to increase its vapor pressure. If you then even more so weaken the intermolecular force, go to a compound that doesn't have hydrogen bonding capabilities like an ether, like diethyl ether, you then have an even lower boiling point, and you therefore at all temperatures have higher vapor pressure. So stronger intermolecular forces lower the vapor pressure at a given temperature. So stronger forces, lower vapor pressure, weaker forces, higher vapor pressure, therefore lower boiling points. So diethyl ether reaches its boiling point closer to 35 degrees C. And then if you go to ethylene glycol is like an ethanol compound that has a second hydroxyl group. So ethylene glycol, we use it as an antifreeze molecule. It has a higher boiling point because now it has two hydrogen bonds on opposite ends of the molecule. So really strong intermolecular forces, and that even more so weakens its, lowers its vapor pressure as a result. So it has a higher boiling point. Okay, that'll be our stopping point for today. Our keyword is Lewis for today. I'll add another minute or two to the quiz to make sure everyone gets them in for the day. But we'll pick up from the rest of chapter 11, get into some review of chapter 10 on Friday, and then next week we'll be into chapter 12 and hopefully then some review for the final exam. If you're still writing anything from the previous slide, I'll post the PDF slides as I've been doing on Carmen. All right, guys, have a great day.